going to be the lecture over section. So we're going to be looking at line spectra and energy levels. So if an atom makes a transition from initial energy E sub I to a lower final energy E sub F, the energy of the emitted photon is going to be Planck's constant times the frequency, where that's going to end up being the difference of those two energy levels. The photon energies of the hydrogen atom's spectral lines are all differences between its energy levels, and the energy levels are going to be given by this mess. So let's go and let's take a look here. Okay, so you've got a continuous spectrum from a very hot light source. In this case, it's a light bulb with a heated filament, a lens, you got a slit, you got a diffraction grating, and then you see a whole host of lines out here. You've got a lamp with a heated gas, and you can see the lines are split a little more finely out here. So we've known that there's line spectra here for a couple of centuries. So a prism or diffraction grating can be used to separate the various wavelengths into a beam of light into a spectrum. If a light source is a very hot, solid, or liquid, such as the filament in a light bulb, spectrum is continuous. In other words, light of all wavelengths is present. But if the source is a gas carrying an electric discharge, like with neon, or if it is a volatile salt heated in a flame, as when table salt is thrown into a campfire, only a few colors appear in the form of isolated, sharp, parallel lines. The position of each line on the screen depends on the wavelength of light passing through the slit. Spectrum of this sort is called a line spectrum. So, by measuring the angle of deflection of the individual lines, one can determine the specific wavelengths and frequencies emitted from the light source. So, early in the 19th century, it's discovered that each chemical element has a definite, unchanging set of wavelengths in its line spectrum. And the identification of elements by their spectra became a useful analytical technique. So, the characteristic spectrum from each element was assumed to be related to the internal structure of its atoms, but attempts to understand this relationship on the basis of classical mechanics, electrodynamics, were not successful. In other words, neither of those techniques are able to discern what's going on. So two key pieces of the puzzle were missing. You've got the photon concept and a new and revolutionary picture of the structure of the atom. It finally took Niels Bohr in 1913 with an insight from a historical vantage point more than 90 years later. Seems almost obvious. Every atom has some internal structure and internal motion, and therefore some sort of internal energy. But each atom has a set of possible energy levels. An atom can have an amount of internal energy corresponding to any one of these levels, but it cannot have an energy intermediate between the two levels. In other words, it's discrete between those two. It can't be somewhere in between. So if the atoms of a particular element can emit and absorb photons with only certain particular energies, then the atoms themselves must be able to possess only certain particular quantities of energy. Bohr's hypothesis is shown here. Bohr assumed that while an atom is in one of these permitted energy states, it doesn't radiate. However, the atom can make a transition from one energy level to a lower level by emitting a photon with energy equal to the difference between the initial and the final. So in other words, an atom drops from an initial level to a lower level by emitting a photon, which is basically a way of carrying away energy that it no longer needs in order to be able to exist. So for the simple atom, hydrogen, Bohr pictures these levels in terms of the electron revolving in various circular orbits. Only certain orbit radii were permitted, and we'll return to this picture a little bit later. So you can see here the energy in the fall here is going to be the difference between those two energy levels. Obviously, it's measured in joules. Here, through this example, if you've got a photon of orange light with a wavelength of 600 nanometers, then you can go through and figure out what its frequency is. Once you know what the frequency is, you'll always know what Planck's constant is, and then you can determine the energy level, which when you measure it in joules, you make the conversion to EV, because at this level, measuring it in joules, it's too large of a unit. Is a scaled down version or scaled down unit of energy that's much smaller, and that's something that we could use for cases like this. Same principle applies when a photon is absorbed by the atom. In other words, basically runs things in reverse. You're going from here up to there. So let's take a look at how this idea can be used with what we do in the spectrum of hydrogen, the least massive atom, therefore a little bit less complicated than maybe some of the others, is something we'll look at here. So under proper conditions, atomic hydrogen emits a series of 4 lines in the visible region of the spectrum. You can see those there in the figure. So the line with the longest wavelength or lowest frequency is the red one, and that's called H sub alpha. The next line is blue-green and H sub beta, and so on and so forth. Gamma and delta. This is considered to be the Balmer series of spectral lines. So Johann Balmer found by trial and error the formula that gives the wavelengths of these lines that are in the visible spectrum, and that's now referred to as the Balmer series. And that's basically how you find the wavelength. So if you take that equation here, you substitute an n is equal to 3, you obtain the wavelength of the H sub alpha line. The R here is going to be referred to as the Rydberg constant. Balmer's formula has a direct relationship to Bohr's hypothesis about energy levels, and if you use these equations, you can find the photon energies corresponding to the wavelengths of the Balmer series. If you multiply that by Hc, then basically you can go from determining a wavelength here to determining energy. So the Balmer series therefore suggests the hydrogen atom has a series of energy levels donated by this. So these energies are negative because we have arbitrarily chosen the potential energy to be 0 at very large values of n. And then that is the state with n is equal to infinity, corresponds to the state where the electron is completely separated from the nucleus. Each wavelength in the Balmer series corresponds to a transition from a state having n equal to 3 or greater than to the state where n is equal to 2. The numeric value of this product ends up being 13.6 eV. So the magnitudes of the energy levels are approximately this. Other series of spectrum lines for hydrogen have been discovered experimentally, and they're named for their discoverers. The wavelengths are represented by formulas very similar to the Balmer formula. One series is in the ultraviolet region, another is in infrared, because again, remember, we were looking at the visible spectrum. All the spectral series of hydrogen can be understood on the basis of transitions from one energy level to another, with the energy levels given by equation 2010. So for the Lyman series, the final state is always n is equal to 1. Paschen series, it's n is equal to 3, and so on. Taken together, these spectral lines give strong support to Bohr's picture of energy levels in the atom. And the relationships of the various spectral series to the energy levels in electron orbits are shown here. So you can see here, Balmer series, we're talking about decays that come down here to n is equal to 1. Paschen, it comes down to I'm sorry, n is equal to 2. That's my bad. Paschen series comes down to n is equal to 3. Bracket series comes down to n is equal to 4. Lyman series, you can see all of these particular types of decays down to level 1. And here's another way to look at it. You can see the energy levels given here. So only atoms or ions with a single electron can be represented by a simple formula of Balmer type. It's always possible to analyze the more complicated spectra of the other elements in terms of transitions among various energy levels and to deduce the numerical values of these levels from the measured spectrum wavelengths. Every atom has its lowest energy level, representing the minimum energy that the atom can have. It's called the ground state. And all states with energy greater than that of the ground state are considered to be excited. A photon corresponding to a particular spectrum line is emitted when the atom makes a transition from an excited state to a lower excited state, or perhaps the ground state. In some cases, an atom can have 2 or more states with different electron configurations, but the same energy. Thus, we'll sometimes need to distinguish between energy states and energy levels. One level can correspond to several states. So the sodium atom has 2 closely spaced levels called resonance levels at about 2.1 eV above the ground state. Characteristic yellow light with these wavelengths is emitted during transitions from one of these levels to the ground state. And conversely, a sodium atom initially in the ground state can absorb a photon with a wavelength of these lengths. After a short time, the atom spontaneously returns to the ground state by emitting a photon in the same way. The average time spent in the excited state is called the lifetime of its state. For the resonance levels, the lifetime is 16 nanoseconds. That's pretty short. Line spectra are produced by matter in the gaseous state in which atoms are far apart and interactions between them are negligible. If the atoms are identical, their spectra is also identical. But in condensed states of matter, there are strong interactions between the atoms. These interactions cause shift in the energy levels, and levels are shifted by different amounts from different atoms. Because of the very large number of atoms, practically any photon energy is possible. So hot condensed matter always emits a spectrum with a continuous distribution of wavelengths and not a line spectrum. And this is called the continuous emission spectrum. So you got a few problems there to work through. And hope you clarify your understanding.